Hello and welcome to Everything Electrical Engineering. In today's video we will analyse the short circuit and open circuit tests of a transformer. From the test we can determine the equivalent circuit, voltage regulation and transformer efficiency. Both tests are explained in detail before calculating the open and short circuit values. MATLAB is used then to verify the results. The equivalent and approximate equivalent circuits are suitable for constant frequency, steady state circuits. The components R1 and R2, X1 and X2, which are the respective resistance and reactance for the primary and the secondary side of the transformer. V1 is the applied voltage and V2 is the voltage across the load terminals ZL. E1 and E2 differ from the terminal voltage as they include the voltage drop across the resistive components. N is the turns ratio, and I1 and I2 are the currents flowing in the primary and the secondary side of the transformer. I1 has two roles. One, it sets up the mutual flux in accordance with Ampere's law, and two, it balances the demagnetizing effect of the load current in the secondary winding, denoted by I and I-2 respectively. The mutual flux has a resistive and inductive component RC and XM, where IC and IM are the respective currents. The flux has three components, X1 and X2 being the leakage flux, and XM the mutual flux set up during energization. The leakage flux is because not all flux is common to both sides of the windings, some escapes and causes a volt drop in the circuit. For convenience we can transfer one side of the winding to the other and refer both windings to that respective side. These will make up the equivalent values for R and X. The formula to refer the secondary components to the primary can be observed. Note, the dash symbol is used when referencing one side to the other. At no load current, the primary volt drop is very small across E1. Thus, the circuit can be approximated by moving the shunt branch to the left side of the components without any real loss in accuracy. We can now combine the resistive and inductive components. We could also neglect the shunt branch altogether, since the excitation current is usually less than 5% of I1. We could go a step further here and neglect the resistive component. Since large transformers greater than 500 kVA have a very small value for R compared to X, we can now say the practical transformer operating sinusoidal steady state is equivalent to an ideal transformer with external impedance branches. However, for the open and short circuit tests, where efficiency and excitation is important, these cannot be ignored and the equivalent circuit will be approximated as outlined. For the open and short circuit test, the voltage is normally connected to the primary and the secondary side respectively. This is basically due to limitations of some measurement devices. For open circuit tests, rated voltage is applied to the primary or the LV side of the transformer. In this example, the rated voltage is 230. As mentioned already, the current I1 has two components. One, the current sets up the mutual flux or energization current I5, two, the current used to balance the demagnetizing effect of the load current I-2. Since I2 is 0, I-2 will be 0. Thus, the only current flowing will be in the shunt branch, I5, which mentioned earlier is generally less than 5% of rated current. Therefore, the copper losses can be considered negligible, and since rated voltage is applied, normal flux, subsequent rated iron losses will flow in the core of the transformer. This can be observed from the simplified graphical representation of the transformer. Now let's look at setting up the metering so one can obtain the necessary parameters. The open circuit test is required to obtain the no load power, PO, the current I5 and the voltage VOC. The auto transformer may not be required where the applied voltage is equal to the rated voltage. Use these parameters to calculate the resistive and inductive components RC, XM and subsequent current IC and IM as outlined in the open circuit schematic. IC is the real power loss which accounts for both hysteresis and eddy currents, where IM is the reactive power loss used to magnetize the core of the transformer. As mentioned already, rated voltage is applied for this test to ensure that the magnetization reactance will be operating at a level close to that which exists under normal operating conditions. The derived values from the open circuit test can be observed. And since these are vectors, we can use phasor representation to determine the values of the shunt or energization currents IM and IC. First, let's determine cos phi 0. And since the iron losses PO are equal to the voltage times I5 times cos phi 0, cos phi 0 is equal to PO over the voltage times I5. which is equal to 1050 over 230 times 9. But since we are more interested in the angle, we can just inverse the cosine, which is equal to an angle of 59.52 degrees. From the phasor diagram we can see IC is equal to I phi times cos phi 0, and Im, the magnetization current, is equal to I phi times sin phi 0. IC is therefore equal to 9 times cos 59.52 degrees, which is 4.563 amps. And Im is 9 times sin 59.52 degrees, which is equal to 7.756 amps. RC is the voltage squared over PO, the iron losses, and XM is equal to the voltage over IM. This is equal to 50.38 and 29.65 ohms respectively. For the short circuit test, the voltage is conveniently added to the HV side. As the current and voltage are inversely proportional, an applied voltage usually between 5 to 15% is enough for I2 to equal rated current. The reduced voltage impacts the mutual flux in the shunt branch, and subsequent iron losses can be considered negligible. Conversely, the copper losses will be the rated losses, as I2 will be the rated current. Therefore, the open circuit test will present the rated iron losses, and the short circuit test will present the rated copper losses. The short circuit test, the parameters to measure are the voltage, VSC, the power, PSC, and the current, ISC. The open circuit schematic outlines the parameters we will be calculating, the R and X equivalent values. The short circuit test determines the copper losses of the transformer. We can use this knowledge to derive the equivalent values. Copper losses, or PSC, is equal to I squared R. Our R equivalent would be equal to PSC over ISC squared. Now use the parameters from the short circuit test to determine the R equivalent. This is equal to 2625 over 50 squared. This is equal to 1.05 ohms. Z equivalent is equal to VSC over ISC, which is 185 over 50. This is equal to 3.7 ohms. And X equivalent can be found by the square root of Z equivalent squared minus R equivalent squared, which is equal to the square root of 37 squared minus 1.05 squared. This is equal to 3.47 ohms. MATLAB was used to verify the results from the open and short circuit tests as outlined. Efficiency of the transformer can be easily calculated or presented graphically with the likes of Excel, MATLAB, or some other program. In this example I used MATLAB to plot the efficiency percentage to power output of the transformer used here. I will do more in-depth MATLAB videos covering all sorts of calculations in the future. Thank you for watching. Please don't forget to check out some of the other videos. If you felt like you got any value from this, please like, comment and share.